Hello everybody. So in this video we're going to continue with chapter 11, Integral Calculus, specifically 11.2, Area and the Definite Integral. So we start with example 11.7, which says, find the area, a of x, between the graph of the function f of x equals 3 and the interval -1, x, and then find the derivative of a of this area function. So what would be the area here? We know that the height has to be 3 because the distance from the x-axis to the top of this rectangle is 3 units. And we also know that the base is x plus 1 since this is -1 here, this point. Therefore, the base is x plus 1. That means that the area is equal to 3 times x plus 1, which would be 3x plus 3. And then notice that they want us to find the derivative. So what would be the derivative of 3x plus 3? Well, it's simply going to be, the derivative of a of x is simply going to be 3. But notice that this is f of x, and this is f of x. So notice that there's an interesting relationship between the area under the curve and the derivative. So next we have example 11.8, and it says, find the area, a of x, between the graph of the function f of x equals 3x plus 2 and the interval -2/3, x, and find the derivative of a of this area function. So the base is going to be x plus 2/3, so 1/2 times x plus 2/3. This is the area we're finding. And this times the height, but the height here is going to be in terms of x. So regardless of what x is, the height is going to be 3x plus 2. But notice that if I multiply this expression by 3, but I also have to divide by 3 if I do that, I'm going to get that the area is equal to 1/6 times 3x plus 2 times 3x plus 2, and this is going to equal 1/6 3x plus 2 squared. Now the reason I'm doing it this way is because it's much easier to find the derivative of this expression by using the chain rule. So what would be the derivative? Well, from the chain rule we know that the derivative is going to be equal to, now notice that we have to multiply by 2, so that would be 1/3 times 3x plus 2 times the derivative of the inside, which is just 3, and this is going to give us obviously 3x plus 2. But notice that 3x plus 2 is again f of x. Very well, so next we have example 11.9, and it says find the area, a of x, between the graph of the function f of x equals x plus 2 and the interval -1, x, and then find the derivative of a of this area function. Remember that the area of a trapezium is equal to 1/2 small base plus large base times the height. So if we flip this around, notice that we can call this here the small base. This would be the large base, and this here would be the height. Therefore, the area in terms of x as a function would be equal to 1/2, and the small base is 1. As you can see here, that's the height there, 1, plus the large base, which is x plus 2, times the height, which is x plus 1. And then here we're going to get that the area is equal to 1/2 times x plus 3 times x plus 1, which again is going to equal 1/2 x squared plus 4x plus 3. Okay, so this would be then the area of what is contained under the curve in that interval, right? Between -1 and x. How about the derivative? Well, if we do the derivative of this, the derivative of this is going to equal simply 1/2 times 2x plus 4, and then this is going to equal x plus 2, which again brings us back to f of x. So notice that in all the three examples we did previously, we had the case that the derivative of the area is equal to f of x. So in general, what this means is the following. If we have a curve that is continuous, so let's make a curve that is continuous here, and we find the area under that curve from a to a value x, and this curve is f of x here. So if this area here is a of x, then if we do the derivative of that, we're going to find the upper boundary of the region, which is the graph of f of x. And this intuitively, what it does is give us the fundamental theorem of calculus, which says that if the area under a curve is equal to the integral of f of t dt. Now this is a function of x. Although it's in terms of t, it's still a function of x. So the integral from a to x would give us the area under the curve. So that means that the integral from here to here would give us this area. But if we do the derivative of that, we're going to get the original function. So basically what this is saying is that the derivative and the antiderivative or integral are the inverses of each other. So next we have some basic properties of the definite integral. One very important property is that if you have the integral of f of x from a to b, this is equal to minus the integral from b to a. This is a very fundamental property that you will find is very useful. Next, that we have that the integral of f of x from a to a is obviously equal to 0. Now, why is that? Well, if you're integrating from a to a, that means that you're not really moving, you're not finding any area. So this would just be 0. Next, we have the case where if you have the integral of any constant k from a to b, that is simply going to be k times b minus a. We can see this graphically in a very easy manner. So if this is the x-axis and this is the y-axis, and you have some constant k, so this is f of x equals k, then if you want to find the area under the curve between a and b, this is obviously simply going to be k, which is the height, times the distance between a and b, which is simply b minus a. So this is just simply finding the area of a rectangle. This property is also, the next one is the same property that I showed you guys with indefinite integrals. If you have the sum of two functions in an integral, you can separate it, right? The sum or the subtraction. Also, you have the case of a function where you have a constant. You can take that constant out of the function, out of the integral, and multiply the integral by that constant. And finally, this one is interesting. If you have a point C in an interval between A and B, then you can say that the integral from A to B of f of x is the same as the integral from A to C plus the integral from C to B. So in example 11.10, they want us to find each derivative. But notice that this is simply a direct application of the fundamental theorem of integral calculus. So for letter A, they want us to find the derivative of the integral from 5 to x of 7t cubed dt. So here simply what we have to do is a substitution. All we have to do is substitute t with the letter x, and we're going to get 7x cubed. B is also pretty straightforward because all they want us to do is the derivative of the integral from 0 to x of dt over 1 plus t to the 4. And again, this is a simple substitution, and it's simply going to be 1 over 1 plus x to the 4. For C, we have a little bit of a difficulty because if you notice that for C, it says from x to pi, and they want us to find the derivative of this from x to pi of the expression 1 over 1 plus t to the 4 dt. So the problem here is that the bottom of the integral, so the left-hand side part of the interval is not a constant. So we need to flip this. But remember that we can simply flip this by putting a negative in front, because this would be the same as saying minus the integration from pi to x of 1 over 1 plus t to the 4 dt. And then now we can simply plug in x and get minus 1 over 1 plus x to the 4. So next we're going to take a look at the second fundamental theorem of integral calculus. So recall that we said that the area function, a of x, is equal to the integral from a to x of f of t dt. Then we have that if capital F of x is any antiderivative of f of x, then applying what we learned earlier, we have that f of x, capital F of x, is equal to a of x plus c, where c is an arbitrary constant. So what happens if we do a of b, right? A of b. Well, we can say that f of b, capital F of b, is equal to a of b plus c. And this is the same as saying the integral from a to b of f of t dt plus c. Notice that all we're doing is substituting x with b in the area function. Okay, if we do f of a, that's going to be a of a plus c, and it's going to be the integral from a to a of f of t dt plus c. But this is the same as saying 0 plus c, because remember that if you have an integral from a to a or from one constant to the same constant, that's just going to equal 0. So then if we subtract these two expressions, if I subtract this from the top expression, I'm going to get that f, capitalized F of b minus capitalized F of a, in other words, the antiderivatives. This is going to equal, and remember that this is just going to be this, this we can eliminate, we can forget about it. We can just go this minus 0 minus c, so we're going to get the expression integral from a to b of f of t dt. Okay, very well. So for example 11.11, they want us to apply the second fundamental theorem of integral calculus in order to be able to evaluate each integral. So for letter A, they want us to integrate from -1 to 3 for x to the 5 dx. So In these cases, we simply do what we would normally do. We would say, well, this is x to the 6 over 6, but this is a definite integral that goes from -1 to 3. So that means that first we have to plug in 3 in the equation, right? So that's going to be 3 to the 6 over 6 minus, and then we would plug in -1. And it's going to be -1 to the 6 over 6. And then if we do the math here, we're going to get 364 over 3. For b, same thing, right? It's an integration, a definite integral from 0 to 4 for the square root of x dx. So remember that we can rewrite this as saying the integration from 0 to 4 of x to the 1/2 dx. So we just have to apply the power rule, right? And if we do that, we're going to get 2/3 x to the power of 3/2. But this one's definite, so we have to go from 0 to 4. In other words, plug in 4 and then subtract after we plug in 0. So notice that this is going to be the same as saying 2/3 times 4 to the power of 3/2 minus 0. And this is going to be equal to 16/3. For c, it's the integral from pi to 2 pi of cosine of theta, derivative of theta. Okay, so the antiderivative of cosine is sine. So this is simply going to be sine of theta, but it's a definite integral, so it goes from pi to 2 pi. In other words, sine of 2 pi minus sine of pi, right? And this is simply going to be 0 minus 0, which is 0. And then finally, we have letter D, which we're going to do after I erase all this. So for D, they want us to integrate from 1 to 2 for the function 4 plus u squared over u cubed du. So this is a typical case where we can separate the fraction into two separate fractions, right? So this would be equal to the integration from 1 to 2 of 4 over u cubed plus, and don't forget du, I always forget that. So du plus the integration from 1 to 2 of u squared over u cubed du, and this is going to equal the integration of 4 times u to the negative 3 du plus, and this is from 1 to 2, plus the integration from 1 to 2 of 1 over u du. And notice that we could rewrite this as being equal to, let's say here, it's going to be 4 times u to the negative 2 divided by negative 2 plus the natural logarithm of the absolute value of u. And because it's a definite integral, it would go from 1 to 2. So notice that here we're going to get that this is equal to negative 2 times u to the minus 2. Or we can rewrite this actually, let's rewrite it as negative 2 over u squared. And this plus the natural logarithm of u. And because we don't have any negative values, we can forget about the absolute value. So this from 1 to 2. So notice that this is going to give us negative 1/2 plus the natural logarithm of 2. And then we're going to do minus, minus, so plus, and it's going to be 2 divided by 1, so that's going to be 2. And then this minus the natural logarithm of 1. But remember that the natural logarithm of 1 is simply going to be 0. So this would cancel out. Therefore, we're going to end up with the expression 3/2 plus the natural logarithm of 2. Okay, so finally we are in example 11.12, which will be the last one on this video. And it says evaluate the definite integral from 2 to 6 of the square root of 4x plus 1 dx. So this is a case where you necessarily must apply u substitution. So notice that we can say, well, let's call u equal to 4x plus 1. And then that means that the derivative of u is going to be 4 dx. So we don't have the 4 dx. Remember that in those cases we would have to go 4 dx, but also multiply by 1/4. Okay, now the other thing that we have to be careful with is the limits of the integration, because these limits that we have here, this limit and this limit, are in terms of x. But because we're going to do this in terms of u, we have to change the limits. But notice that for the bottom limit, if we plug in 2 into this here, we're going to get 4 times 2 plus 1, which is 9. So that's going to be the lower limit. And then if we do u of 6, that's going to equal 25. So this is going to be the upper bound or the upper limit. So notice that then we can say that the integration from 2 to 6 of the square root of 4x plus 1 dx is going to equal, and once we do the u substitution, it's going to be 1/4 of the integration from 9 to 25 of the square root of u, but I'll just write it as u to the 1/2, u to the 1/2 du. So this is simply going to be 1/4, and then this times 2/3, u to the 3/2, and it's bound, right? So from 9 to 25. So we're ready, right? Because this is simply going to be 4 times 3, but there's a 2 here, so it's going to be 1/6. So 1/6 times, if we plug in 25 and we do all the math, we're going to get 125 minus plugging in the 9, we're going to get 27. And if we subtract this and then multiply, we're going to get 49/3.